Morning. Now we'll start with this question. We have to find expected present value and standard deviation of present value of a 25-year endowment policy with sum assured of 10,000 payable at the end of the year of death or on maturity. Now when the policy ends, we say it is matured. Okay, so that is why the term maturity. For a life aged 40, okay, basis is AM92, ultimate 4%. Okay. So what we want is 10,000 A 4025, right? This is what we want. Okay. So A 4025 would be A 40-25 plus V raised to 25, 25P 40, and A 40-25 A40 minus V raised to 25, 25P 40, A65. Let's find these values. Same 92, L values, rate of interest was 4%, so L65, L40, this is our AM92 4%. We want A40, okay, A40 minus answer into A65. The term assurance or term assurance value. This much into 10,000. So the expected present value. Okay, I did not write stuff. Okay, no, this is correct. No problem. Expected present value is going to be 3890.69. Now for standard deviation, first we'll have to calculate 2A 4025. Okay, 2a 40 25, that would be 2a 40 dash 25 plus v raised to 25 into 2, that would be v raised to 50, 25p 40. Okay, two a 40 dash 25 would give us 2a 40 minus v raised to 50, 25p 40, a 2a 65. Okay, so v raised to 50, 25p 40. So I already have v raised to 25, 25p 40. I can just multiply another v raised to 25 to it. Okay, so I have 0.335725 into 1.04 raised to another 20, minus 25. We'll get 0.125936. Okay, and let's calculate this. To A40 we have here 2A65. Okay, so 0.0290624, this much, plus 0.125936 will give us this much. Okay, so variance of present value will be equal to 10,000 square to a 40 25 minus a 40 25 whole square. I did not do 10,000 square. So variance is 362373.315. We want to find standard deviation. So we'll take root of this. And the standard deviation is 601.3. 97. So here we were finding the expected present value and the standard deviation for an endowment policy for a person age 40 going for 25 years. Okay, so 25-year endowment policy for a person age 40. Now, for such cases, we have specific endowment tables as well. If I go further, okay, if we go 3 pages further, on page number 100, you will see for 4%, we have a table where they have directly given us our endowment value, okay, AXN. Now this is specifically for n is equals to 60 minus x. Now what they have done is, rather than giving you all possible values, they have given you for the most common values. So n is equals to 60 minus x. That just means that whatever age and number of year of policy or the term of policy you are taking, that should add up to 60. All of those values are given in this table. So basically x plus n is equals to 60. Okay. Now in this case, if we just add up our x plus n, you will find it is 65, right? 40 plus 25 gives us 65. Next page we have that as well. In next page, that is 101, for 4%, you will see we have n is equal to 65 minus x. Okay. 65 minus x for different values of n, this is n. Okay. So n we want 25, this is 25. You can see the other side x is 40, 25 and 40. But we cannot find variance using this. We can only find the expected present value. Okay. So you can see that A 40, 25 is given as 0.38907. 0.38907. And what did we get? 38907, right? So we got the same value as well. So you could have directly taken this value from here. Correct? So in case of x plus n being 60 or x plus n being 65, we have tables where we can directly find the endowment value. Okay. You can use this endowment value to find the term assurance as well, because term assurance can be written as our endowment minus pure endowment. So you can definitely use this to find the term assurance. It's just slightly faster or slightly easier than our whole life. Okay. So we have two methods of finding term assurance for certain cases, not for all cases. Of course, for other cases, we will be using just whole life. That was AX minus V raised to N NPX AX plus N. So this will be used only for X plus N equal to 60 or 65. This is for all cases. Then I've talked about that we have 4% as well as 6%. So see, there are set of tables all for 4%, right from page number 96. We'll be using this 4% tables till page number 101. You scroll down, I think till 101. Yeah, till 101 we have all 4% tables. You can see it on top, they have written 4%. After 101, that is 102, you will find the tables are exactly same tables you will find for 6%. So for 6% rate of interest also, they have given us tables, exactly the same tables for 6%. So we get sometimes confused and take 4% for 6% or 6% values for 4%. Just be a little bit careful which tables are we referring to when we are solving our sums. Okay. Now in all of these cases, all the 5 different assurances that we saw, we took that our benefit is payable at the end of the year of death. Now in practical life, we talked about this, that a person might not be, the family might not be waiting for so much time so that the payment will always be given on 31st December, right? You can imagine if the death occurs on 1st January, it will be almost 1 year wait for 31st December. In practical life, it usually takes anywhere from 15 days to 3 months to get the payment. Okay, company processes okay after the claim is made, and usually it takes about 15 days to 3 months. Now here what happens is that we will be assuming, theoretically we will be assuming that is happening immediately on death. Okay, so payment occurs or benefit is payable immediately on death. So for that we will calculate whole life assurance. Okay, so I will not write the definition because the only change in the definition is going to be that instead of at the end of the year of death, the term becomes immediately on death. Okay. So when we are talking about the payment, the benefit is given immediately on death. That means the random variable, the number of years a person might live for, the number of years a person might live now becomes a complete future lifetime random variable from current date, right? So here we'll say our present value will be equal to v raised to tx, where tx can be anywhere between 0 to infinity. Okay. So immediately on death the payment was given, so we'll discount it to 0 and that becomes our present value. Our expected present value, expected present value, we will take it in terms of integration going from 0 to infinity. We'll have v raised to t, and then we'll take f of t dt. Okay. That gives us integration 0 to infinity v raised to t tpx mu x plus t. This again we learned in chapter 15, okay, dt. This we will write it as a bar x. Okay. So because sort of we are paying continuously throughout the year, every possible time in the year the payment is given. That is why it is sort of continuous, but we'll never call it as continuous. It is payment immediately on death. Okay, whole life payment immediately on death. Okay. Now similar to yesterday, if I want to find expected present value square, okay, if I want to find expected present value square, all I have to do is square the present value here. Okay. So I'll have integration 0 to infinity v raised to 2t. We'll have tpx mu x plus t dt, and we'll write it as 2a bar x. So what are we seeing here? We are saying payment given at time t for a person who survived at time t and then died immediately at that age. Okay. Survived till time t and then died immediately at that age, the payment would be given to that person. and we are adding all such cases from time 0 to time infinity. Okay, add all such cases from time 0 to time infinity. Okay. Here again, this is nothing but a bar x at the rate of I dash, right? It's the same thing. Variance of present value will be 2a bar x minus a bar x whole square. Now, unfortunately, we do not have any tables for a bar x, right? We do not have a value because in real life, we will be collecting values of every year. Okay, like here, whenever tables are given, we have taken into account year, 1 year at a time. We have not taken any values in between. The reason is because this is more practical to collect the data as well as more practical in terms of actual values we might find in the future. Okay. So we need an approximate way to relate it to this. Okay. So we say, if we assume that there is a uniform distribution of death, okay, uniform distribution of death throughout the year, okay, we say assumption uniform distribution of death throughout 1 year, then we can assume that all of the payment are basically averagely paid at the middle of the year. Okay. Okay. So therefore, we can say all payments averagely paid in middle of the year. Okay. If we take that assumption, we'll say our a bar x will be approximately v raised to half payment paid in the middle of the first year if the death occurs within the first year. If the death occurs within the first year, all that payments are paid in the middle of the year. Plus v raised to 3 by 2, that means 1.5. I'll just write it as 1.5. It's just easier, right? 0.5, 1.5, it's just easier. Paid in the middle of the second year if the person survived for 1 year and died within the next year. That means died within the second year. Then the payment is given in the middle of that year. Similarly, 2.5 for a person who survived for 2 years and then died within the third year. This goes on forever. Okay. Now, if I multiply and divide v raised to half, so 1 upon v raised to 0.5, I will get v qx plus v square px qx plus 1 plus v cube 2px qx plus 2, and this goes on forever. This becomes equal to, let's say, 1 plus I raised to half, and this would be AX, payment at the end of the year. Okay, payment at the end of the year. Okay. So our A bar X approximately is equals to 1 plus I raised to 0.5 AX. And using the same relation, we can say that our 2A bar X will be approximately 1 plus I times 2AX. Okay. So this is the relations that we will be using to figure out our values when we have payment immediately on death. So you'll see we will be studying a lot of formulas, like 20 to 30 formulas each chapter. So that is why I'm saying writing down formulas each day, each time when we are studying, and also revising everything to understand how we use them is going to be very important. If you don't, you will start forgetting stuff and getting confused. Okay, so every day revising everything would be advisable. Okay, so immediately on death, we will be taking approximately, because these values are not very easy to generate. Okay, of course we can generate mu x plus t in terms of age or time, x or t. Okay, and using this we can definitely find what our tpx is going to be, because we know our tpx is nothing but e raised to minus of integration mu x plus s ds. Okay, this is going from 0 to t. So we can definitely generate all of these values if we know mu. Mu is nothing but our force of mortality. Right? But force of mortality, because we are collecting data yearly and we are collecting the real life data, the chances that we can convert it into mu is difficult. And then after generating mu, it will be in terms of time. It will be in terms of how many number of years have passed from that age x. So we will have mu in terms of some complex function of time. Okay, some function of time. Let me write it as g. Okay, and then this will also be some function of time, because we have e raised to minus of integration mu t. And then integrating that becomes almost impossible. Okay, at least for us, the level of integration that we have studied, it becomes very complicated for us to solve them. Okay, there might be different ways of solving them. Okay, but at least we have not studied them. Okay. So that is why we don't get such questions. We do get such integration style questions in this, but we will be talking about them later. Okay. So we'll be using this approximation a lot. Let's talk about term. Term assurance, again, payment immediately on death, and we said that present value would be exactly same as whole life when a person dies within n years. If the person dies after n years, then nothing would be given. Okay. Expected present value, it will be exactly same as whole life only difference will be that we will be going from 0 to n. We are going from 0 to n. and we will write it as a bar x dash n. Okay. And our a bar x dash n can be written approximately as 1 plus I raised to half of a x dash n. That just means it would be 1 plus I raised to half ax minus v raised to n npx a x plus n. Okay. This is going to be our approximate relationship. Then expected present value square will just be integration 0 to n v raised to 2t. Present value becomes squared. So I'll have tpx mu x plus t dt. We'll write it as 2a bar x dash n okay, and we know our 2a bar x dash n will be 1 plus I times 2a x dash n, and our variance would be 2a x dash n minus ax dash n, okay, everything bar whole square. Okay, bar and bar. Let's talk about deferred whole life. So when we talk about deferred whole life, we know that it is starting after certain number of years. Okay. So deferred whole life, our present value becomes 0 when a tx would be less than n, and v raised to tx when tx is greater or equal to n. Okay. So our expected present value is going to be integration n to infinity v raised to t tpx mu x plus t dt, right? So we'll just say that is v raised to n npx a bar x plus n, right? We have done this before. That will just be approximately equal to v raised to n plus 0.5. Okay, or I'll write it here, approximately equal to v raised to n plus 0.5 npx ax plus n. Let's talk about pure endowment. In pure endowment, because benefit is payable only on survival, there's no relation with payment on death. So whether the payment is immediately on death or whether the payment is at the end of the year of death, that should not make any difference. So pure endowment, because this is payment on survival only, we get exactly the same answer when we come up to finding the expected present value. So the expected present value will be payment at time n given for anybody who survives that time n. So a bar x n dash will be equal to a x n dash. In pure endowment, payment given immediately on death or payment given at the end of the year of death does not make any difference. Okay, does not make any difference. We know endowment is term plus pure. So we'll say a bar x n must be a bar x dash n plus a bar x n dash. That is basically a bar x dash n plus v raised to n npx. Okay. So this would be 1 plus I raised to half. Okay, I made a small mistake here. This should be minus because we get 1 plus I raised to half outside. This should be v raised to n minus 0.5. Just make sure in deferred we write it correctly. This is what we get. We can also make the relation in terms of okay, just leave it like this. If you want to make it in terms of the endowment, have 1 plus I raised to 0.5. This can be written in terms of endowment. So I'll have a x n minus v raised to n npx plus v raised to n npx. Of course, I prefer using this. It's just easier. Any problem here? So let me make a question. Now we are talking about find the expected present value of a 15-year endowment policy with 5,000 sum assured payable immediately on death or on maturity to a life aged 45. So you can see we have payment immediately on death. So our expected present value must be 5,000 A bar 45 15. Okay. So 45 15. Let's say that is A bar 45 15 can be written as A 1 plus I raised to 0.5 A 45 15 45 dash 15 plus V raised to N NPX, okay, or V raised to 15 V raised to 15 15P 45. Okay. Now because this adds up to 60, I can actually use the endowment table to find this term assurance. So A 45 dash 15 can be used to find A can be used by the endowment value. So A 45 15 will have minus V raised to 15 15P 45. So let us just calculate this V raised to 15 15P 45 separately. So first of all, rate of interest is now 6%. So I will have 1.06 raised to minus 15 and then into the L values. If 45 and 15, 45 and 15 makes 60. So L 60 45 and for this I will take the endowment table. So first of all, the 6% table starts from page number 102. First I'll go to those tables. Okay, so these are all 4% tables. To go to, these are 6% tables. See, these are 6% tables. Now starting from 102, I need to go to the endowment table for the 6%, where our x plus n must be 60. X plus n must be 60, and we are talking about 6%. Okay, 6 plus n 60. I am looking for age 45, age 45 and 15 years. Okay, age 45 and 15 years, that is so the endowment value is 0.42556 minus answer. This is the term value 0.031035, then plus this. And then into 5,000. Any problem here? Okay. Now, whenever they might ask us to um, solve it without this approximation, they will give us force of mortality, and force of mortality they will give us constant force of mortality. So I'll just take mu x, that is our constant force of mortality. I will say, let's say is 0.07. Okay, so in this case you can see clearly that we have a constant force of mortality that is not dependent on x, it is not dependent on t, so it is constant. Okay, so using this constant force of mortality, let's find a 45 endowment value. So for this endowment value, again I will have to write, okay, and let's say delta is equals to 9%. Okay, so we have constant force of mortality and we have delta given to us. Okay, so if I want to find A45, first of all I will find, say A45 must be equal to A40 dash 5 plus V raised to 5 5p 40, right? So for A 40 dash 5, that becomes integration V raised to t, going from 0 to 5 because we are going only for 5 years. V raised to t tp 40 mu 40 plus t dt. This is our formula. Now mu 40 plus t is just mu x, that is this, because we have assumed constant force of mortality. In real life, force of mortality will never be constant, it will be depending on age, but for the sake of understanding we are taking it as constant force of mortality. We'll have to calculate what TP 40 is going to be. Okay, so TP 40 will just be e raised to minus integration 0 to t mu x ds. Okay. So mu x is just a constant, that is 0.07. So this just becomes e raised to minus 0.07 t. So a 40 dash 5 would be integration 0 to 5. I can write v raised to t in terms of delta. We know v raised to t is just e raised to minus delta t. Okay. So e raised to minus 0.09 t. Then this is tpx, e raised to minus 0.07 t. And mu is just 0.07. So 0.07 comes out and I will have integration 0 to 5 e raised to minus 0.16 t dt. then v raised to 5, 5p 40. All I have to do is for 5p 40 put 5 here, and v raised to 5 we know is e raised to minus delta into 5, and then this will be e raised to minus 0.07 into 5. Delta is again 9%, so we'll get minus 0.16 into 5. And therefore our A 45 will be equal to this plus this. Okay, bar. Did I forget bar everywhere? Because these are all continuous, just put bar everywhere. Just go through everything that we studied today. I'll be back in 1 minute. Yeah. So we studied assurances for a few cases. Okay, whole life. These are the basic policies that we see: whole life, term assurance, endowment. Okay, pure endowment very rarely we see by itself, but these are the main three ones: whole life, term assurance, and endowment. Okay, deferred, usually it is deferred whole life or maybe deferred term. I have never seen deferred term, but deferred whole life is the most common one. That is why we studied that. And we studied how do we calculate the cost that the company will incur. Okay, expected cost the company will incur per policy holder. Okay, this was per policy holder, how much cost the company would incur for a certain what do you say, for a certain sum assured. Okay, so this became nothing but the cost the company would incur if the person if they gave sum assured of 5,000 for an endowment policy to a person age 45, endowment policy going for 15 years, and the benefit is payable immediately on death. Okay, so this is how the policies are designed. These are the main points of this policy. Now what happens is, the other part is that not everybody might be able to just pay the cost upfront. Okay, so what happens is, we sometimes need to calculate premium that are not going to be one time payable, right? Usually whenever we are talking about an insurance company, they will be charging you premium in installments. So maybe per annum, or maybe quarterly, or maybe monthly. These are usually the terms. Okay, because usually the sum assured is high, and then that is why the cost becomes very high, right? So not everybody will be able to pay one time payment, but if we make it yearly payment or maybe monthly payment, it becomes easier and the cost becomes smaller, or at least the one time cost becomes smaller, right? So our chapter 17 is life annuities. Okay, so if we have payment multiple times a year, or sorry, multiple times we will be calling them as annuities, installment payments, right? So in this case, we are going to take the life annuities. That means we will be taking the life portion also. That means the probability portion as well in these annuities. Okay. So these life annuities are used in two different ways. Okay. So simple examples would be premium. Premium is paid by a policyholder from the point the person takes that policy to maybe a certain number of years or till death, whichever comes earlier, right? So premium is paid in terms of annuity. Multiple values will be paid till death. Or the other example would be pension. Pension is again the same thing. A person after a certain age, let's say age 60, starts getting pension. That would be a certain amount every single month till death. Okay. In both of these cases, the uncertainty part is we don't know how many values will we get in terms of premium or will we have to pay in terms of pension, right? So these are all annuities till a certain point, that is till death. Okay. So there can be many different kinds of annuities. You can create such a annuity yourself. Let's say you win a lottery, okay, of let's say whatever a big amount. Rather than using that big amount today, what you can do is you can give it to a insurance company and say that take this amount, invest it however you want, and then give me this much amount every single month so that I have a certain income for the future. Okay. So they will calculate how much will that be according to these life annuities. Okay. How many number of years you might be living from this point, and then calculating how much per month payment can be calculated, okay, in terms of the annuity. So when we talk about life annuity, similar to our normal annuities, it can be payable either in advance, arrears, or continuously. Okay. This is also payable in advance, arrears, or continuous. The first one we'll call it as whole life annuity. Whole life annuity, we'll say, okay, first we will take it as advance, payment in advance. So we'll say an advance annuity of ₹1 payable to life aged X. Okay. Now in this payable to or payable by, it depends on whether we are talking about premium or whether we are talking about pension or different annuities, does not matter. Okay. Payable to life age X. Okay. We have already said when, so it is advance. Okay. Till death. Okay. So the payment goes till death. In assurance, what used to happen is the payment is given only on death, right? Either immediately on death or at the end of the year of death, right? So there was only one time payment for one policy holder. But here we have multiple payments, right? We have here multiple payments. So person age X, so we'll say if, I'll make, so here let's say the person lives for 0 number of years. If the person lived for 0 number of years, that means dies within the first year. If the person dies within the first year, the payment of 1 was given at time 0, right? At time 0, the payment of 1 was given. So the present value becomes 1. Because the payment is given till death. If the death occurs somewhere here, the next payment will not be given, right? And we will be assuming that the death occurs between that year itself. Okay. So next, if the person survives for 1 year and dies within the second year, then 2 payments were given. Okay. 2 payments were given. That would be 1 and then discount 1 more year. Okay. Or I can call it as A due 2. So the present value becomes A due 2. Similarly, if the death occurs in third year, that means survived for 2 years and died within the third year, 3 payments were given. Okay. And this becomes nothing but A due 3. So if I want to make, if the person survives for K years, I'll get a present value as A due K plus 1. So the present value is actually A due Kx plus 1. Any problem here? So our expected present value will be equal to summation values going from 0 to infinity. We will have A due K plus 1 Kpx Qx plus K. So if the person survives for K years and dies within the next year, the payment of this much would be given to that person. We write this as A due X. Now here where the confusion starts, because we have been using this A due N a lot, but we had annuity angle. Here we do not have an annuity angle. So when we write annuity angle, it becomes level annuity for n years. When we are writing A due X, X is here age. X is age. Okay. So don't get confused. So that is why if you miss annuity angle, it will be assumed it is a life annuity. So don't do that as well. Now there is another way of looking at this. So one way is this: how many years a person survives and how much payment would be given to that person. Or second way would be which payment given to which person. Okay. So from the company's point of view, I'll say, let's say there are 10,000 people that bought this policy. Okay. So 10,000 people, the first payment, that is at time 0, was given to everyone because everybody bought that policy was alive at time 0. But at time 1, not everybody was alive. There were some deaths in first year. So let's say 998 people were alive at time 1. So only 998 people got that, annuity of 1. So in first year we had to pay 1000 because everybody is alive. Second year we had to pay 998. I will have to discount this for 1 year. Let's say next year again, let's say 5 people die. So 9903 I will have to discount for 2 years. Again 9000, let's say 87 we raised to 3. So these are nothing but how many people are alive at what time, and I will be discounting all of these payments. So in terms of probability, all I have to do is divide everything by 1000 and I will get basically the probability of a person being alive at what that time. Of course, in terms of theoretical terms, we'll write our expected present value, or our expected present value can be written as summation k going from 0 to infinity. We'll say it is v raised to k, payment given at time k, kpx, to a person who is alive at that time. So to a person who is alive at that time. This is also our a due x. This is also a due x. Any problem here?
Can you explain one more time?
Yes. So from the point of view of cash flows, how much cash flow given at what time? So we as a company would be paying, it's a time, forget about ages now, time 0, 1, 2, 3, 4, whatever. We'll be paying certain amount here, we'll be paying certain amount here, certain amount here, certain amount here, certain amount. How much will we pay depends on how many people are alive. So let's say 1000 people bought the policy at time 0. So because our policy is payable at advance, we will be paying 1000 people 1000 rupees, right? 1 rupee each. Okay, because everybody would be alive at time 0, right? As soon as they buy the policy, we will pay them money. Then at time 1, certain people would die. So let's say only 998 people are alive. Okay, so 2 people died within the first year. So we will be paying only 998 only to the people who are alive. Then at time 2, between time 1 and time 2, let's say 5 more people die. So 993 people are alive. So we are paying them only 993. This is our cash flow. This is our outflow, expenses that we are incurring, right? This is how much we are paying to the policyholders. So what we are doing here is we are saying payment of 1 given to everybody who is alive at that time. Okay. And we will be discounting v raised to k. And instead of taking the number of people alive, what we will do is we will calculate the probability of being alive at that time. KPX. If a person is alive, gets a payment of time k. Is that clear?
Sir.
It's clear now, right?
Yeah, it's clear.
And we are adding all the cash flows. So we are adding all the cash flows then, discounted cash flows. So that is the summation. So there are 2 ways of looking at this, and both are important. Depending on how we are taking the case, this might be important or this might be important. Okay. Here, let's find the variance as well. So now, before we used to find expected present value square and then use that to find variance. Now here we will be using variance of our present value. We will use the formula of variance of our present value. And I hope you have watched the videos, basic videos, because here we are going to use the knowledge about variances, the properties of variances to solve this. Okay, so we will have variance. This is just going to be A due kx plus 1. This is nothing but our level annuity. Variance of 1 minus v raised to kx plus 1 by delta. Whenever we take out a constant, square comes out. So this would be 1 by delta square, variance of 1 minus v raised to kx plus 1.
So isn't it d delta?
Sorry, d. My mistake. D. Right? And whenever a constant is added or subtracted, it does not make any difference in the variance, so I can remove it. So I'll have 1 by d square, variance of v raised to kx plus 1. Now this is present value of whole life assurance. This is present value of whole life assurance. So we know variance of present value of whole life assurance, right? We know the present value of whole life, variance of present value of whole life assurance, that becomes 2ax minus ax square. This becomes variance of annuity due. Okay. Let's talk about arrears. Whole life assurance in arrears. Whole life annuity in arrears. So in arrears, what happens is, payment would be definitely 1 for anybody who survives the first year, right? So when I say my kx is equals to 0, that means the person does not survive for the first year. The present value for that will just be 0. There will not be given any amount for a person who does not survive the first year. Then if the person survives the first year, the payment of 1 would be given at the end of the first year. And the person dies in the second year. When I say kx is equals to 1, we are saying the person survives for first year and dies within the second year. Okay. So the only one payment would be given. I can say it is A1. Similarly, if the person survives for 2 years and dies within the third year, 2 payments would be given. That would be A2. If the person survives for 3 years and dies within the fourth year, that is k is equals to 3, we will have 3 payments in arrears. So A3. Similarly, if the person survives for k number of years, we'll get AK. So the present value becomes AKX. So present value. So the expected present value, we will write it as summation k going from 0 to infinity. We'll have AK KPX QX plus K. We will write this as AX. Now let's see the other way. In the other way, we'll say the first payment, that is at time 1, would be given to anybody who survives the first year. Second payment of time, given at time 2 would be given to a person who survives the second year. So again, payment at time K would be given to a person who survives time K. So we will add up, but in this case, the payments are not going from 0 to infinity. The payments are going from 1, 2, 3, 4 and so on. So K is going from 1 to infinity. This is also written as RAX. Let's talk about variance.
Sir, why in the first case we have K is equal to 0 to infinity, sir?
K was the
No.
time of payment.
No, in arrears, sir, in arrears.
In arrears, see, this K is different from this K. This K is number of years a person survives after age X.
Okay,
So the death can be at time 1, right? That means between first year. So that means the person can survive for 0 number of years.
okay,
This
sir,
K
okay.
is the time of payment. Okay.
Okay, sir.
So because
okay.
we are using the same variable, that might be a little bit confusing. Okay, but unfortunately that is how we use, right? So variance here, variance of this present value would give me 1 minus V raised to kx upon I. Now unfortunately we do not have anything in terms of V raised to kx. So what we'll do is we want to make it into V raised to kx plus 1, because again this is our whole life assurance present value, right? We know this, we don't know what is V raised to k. So what we'll do is we'll multiply, divide both numerator and denominator with V. We'll have 1 minus, so actually V minus V raised to kx plus 1 upon IV. IV is nothing but delta. IV is delta. So D, again I am using the word delta, it is D, right? So I'll have variance, IV is D. V minus V raised to kx plus 1 upon D. So again D comes out and V is just a constant, so it does not make any difference. This will just be 1 by D square, variance of V raised to kx plus 1, and therefore the variance becomes 1 by D square. This is just again present value of whole life assurance. To AX minus AX square, right? So the variance of whole life annuity in advance as well as whole life annuity in arrears is exactly same. Why is the variance same? Because variance comes due to the uncertainty of the payments, right? Due to the uncertainty of the payments, the uncertainty comes because of the uncertainty in terms of mortality. We don't know when a person might die. So that is the uncertainty in this case, and that is why we have variance here. If we knew exactly when the cash flows are going to be, we would not have calculated expected present value and variance of present value, because then we would have just calculated the present value like we did in our previous chapters. So the uncertainty comes because of the uncertainty of the mortality rate, right? We don't know when a person might die. So therefore we cannot calculate how much money we will have to pay at what time. Okay, so therefore we took probabilities. So the uncertainty comes because there is an uncertainty of probability of mortality. Okay, so when I talk about a du x was summation k going from 0 to infinity v raised to t v raised to k, kpx is going to be, if I just write it down, when k is 0, I'll get 1 plus v px plus v square 2px plus v cube 3px, and this goes on forever. Similarly, if I write ax was summation k going from 1 to infinity v raised to k kpx. So the only difference is k is equals to 0 is missing here, right? Otherwise all other values are given. So that becomes v px when I put k is equals to 1 plus v square 2px plus v cube 3px. This goes on forever. So the only thing missing is 1, and 1 is a constant, and we know constant does not make any difference when it comes to the variance. There's no uncertainty in constants. Constants are certain. The variance, the variability is coming from this probabilities. Thus probabilities might not be exactly the same. So because 1 does not have any probability, that is why it's a constant, and that is why it does not make any difference when it comes to the variance, and therefore the variance of whole life annuity in advance as well as in arrears are exactly same. Okay. Now looking at this, we can also easily conclude that our ax is nothing but a du x minus 1, right? Very straightforward. So very important formula, because in our table book everywhere they have given us a du x. From a du x we can easily calculate then ax. You can see here AM 92 6%. You can see besides ax we have a du x. So we have this a du x value given, we can easily calculate our ax value from it. Okay. Any problem here? Let's talk about payment in continuous. So the present value for this would be simply a bar tx, where tx is going anywhere between 0 to infinity. So payment continuously given till time of death, exactly till time of death, and then we are stopping because we are giving continuous payment, right? So the expected present value will just be integration going from 0 to infinity. We'll have a bar t tpx mu x plus t dt. So person alive till time t and then immediately dying at time t would get this much payment, and we will add all such payments. Okay, we'll be adding all such payments. This we will write it as a bar x. Of course, there's another way of writing this. Expected present value can also be written as integration going from 0 to infinity v raised to t tpx dt. Again, this comes from the payments. Payment at time t would be given to anybody who survives time t. And we will add up all such payments. So again, here we are adding up all payments. Here we are adding up all people who survive till time t and then dies immediately. Okay, so payment to those people, the present value of the payments to those people. This is also our a bar x. Variance a bar tx. Delta comes out, 1 does not make any difference, so I will have 1 by delta square variance of v raised to tx. This is again present value of whole life assurance. Just payment is going to be immediately on death. That's the only difference, right? So this would become 1 by delta square 2a bar x minus a bar x whole square. Okay. Then we assume that the payments are going to be, in middle of the year and stuff, and we have an approximate relationship. A bar x is approximately equal to a du x minus half. Okay, a du x minus half. This is an approximate relationship. How do we get it is not important. You can just imagine that we have assumed that the payments are in the middle of the year and done some approximation to find this value. Now in assurances, we had so many different cases. We had whole life, we had term assurance, we had deferred whole life, we had pure endowment, we had endowment. But when it comes to annuity, life annuity, we have only two. One, we have either whole life or we have temporary. We have either whole life or we have temporary annuity. Okay. So advance. We'll say benefit or an annuity or an advance annuity. Advance annuity of ₹1 payable to a life aged X. So payable to a life aged X till death or till n years whichever is earlier. So we are saying instead of going till till death, if the death occurs before n years, then yes, we will be going till death. But if the death occurs after n years, we'll be paying only for n years. So again, till death, till n years, it is same as our whole life annuity. But after n years, it is different. So here our present value will be a due kx plus 1 if our kx is less than n years, and we'll have a due n because exactly till n years the payment would be given if kx is greater or equal to n. So we say PV, present value would be nothing but a due, we say minimum of kx plus 1 comma n. So whichever is lower in this, that is the place, that is the time when we will be stopping the payments. Whichever is lower. If kx plus 1 is lower, then we stop at that time. If n is lower, then we stop at that. So expected present value, we'll say it is summation k going from 0 to now n minus 1. Okay. So if the person dies within survive for from 0 number of years to n minus 1 years, the payment would be this. Okay, so we'll say it is a due k plus 1 kpx qx plus k. Okay, this is what. But if the person survives more than that, okay, if the person survives more than that, then this is the payment. So a due n would be given to anybody who survives more than n years. That means npx. If the person survives n years, then the payment of a due n would be given. This we will write it as a due for age x going till n years. It's called as our temporary annuity. Now exactly same as what we did in whole life, we can write these in terms of number of payments. Number of payments going from k equal to 0 to n minus 1. So anywhere between time 0 to time n minus 1, the payment would be given at time k to anybody who survives time k. Okay. So payment given at time k if for anybody who survives time k. This is also a due x n. What about variance? Now this, even though we have not written, but this is nothing but present value of endowment assurance. Okay, this is nothing but the present value of endowment assurance, because it says payment at what time. So there's a one payment, therefore discounting of only one payment at time what? Minimum of kx plus 1 or n. So either at the end of the year of death or at time n, whichever comes earlier. That is why it is minimum of those things. So it is nothing but present value of endowment assurance. So the variance would be 1 by d square 2a xn minus axn whole square. So in terms of writing, in terms of variance, it is similar, or even in terms of present value, it is similar to an endowment assurance. Okay. A due x n is nothing but summation k going from 0 to n minus 1 v raised to k kpx. We know if I want to convert this into whole life annuity, we know whole life annuity a due x will be summation k going from 0 to infinity. Otherwise this is just same, v raised to k kpx. It's just going from 0 to infinity. If I want to complete this, I will be adding or subtracting, adding and subtracting values k going from n to infinity. V raised to k kpx. The one that I add makes this go from 0 to infinity, and the one that I subtracted will stay as it is. Then we will take m, we will write it as k minus n. The first term is just a due x. The second term becomes summation m going from 0 to infinity v raised to m plus n and m plus n px. We know m plus n px can be written as npx m px plus n. So I'll get a due x minus v raised to n npx outside and summation m going from 0 to infinity v raised to m mpx. This is basically this. Okay. mpx plus n rather. Okay, so this becomes a due x minus v raised to n npx a due x plus n is exactly the formula that we get for term assurance. So temporary annuity formula in terms of calculation would be exactly same as a term assurance formula. Even the deriving of the formula was exactly same what we did in our term assurance. So you have 15 years advance annuity payable to life aged 45 till death or maturity, whichever is earlier. So this is nothing but our temporary annuity. Okay, so we'll say A due 45 15 will be nothing but A due 45 minus B raised to 15 15p 45 A due 60. Let's calculate that. So first of all, we are looking for rate of interest is 4%, right? I took 4%, yes, 4%. So let's go to 4% tables. 4% tables. Here we are. Okay, 4% tables. We are looking for A due 45. A due 45 gives me 18.823 minus V raised to 15 15p 45. We'll calculate that. First I will take A due 60. A due 60 would be 14.134. Just keep this in mind. Assurance will always be less than 1 and annuity will always be more than 1. Okay, so if you are confused which table is for which, okay, if you remember that when we are solving annuity, the value will always be more than 1, and when we are talking about assurances, the value will always be less than 1. So you'll not get confused there. Okay, V raised to 15, so 1.04 raised to minus 15, and then into, we want 15p 45. So L 45 and 60. So L60 is 9287.2164 by 45 9801.323. So this is the value 11.3865. 654. Now just because we have these values adding up to 60, for 60 and 65 we also have those tables. In endowment table they have also given us temporary annuity. Okay. So if we go down, so this was our normal 4% table. If we go down, these are the endowment style table. You can see we have temporary annuity as well. A due X and 45 15, because total is 60. I am looking for N is equals to 60 minus X table. In this I want 15 years and age 45. You can see 11.386. 11.386 is exactly what we got here. So again, in the case of 60 and 65, we can definitely use those endowment table to find temporary annuity. So we'll end our class here today, and do revise everything, because as we go further things are going to just get complicated, because we'll be adding more and more stuff. Okay, so tomorrow we will still have class. So every Monday from now we will have class 6 to 8 p.m. tomorrow. Okay, we'll be continuing this. So that is why I'm not giving you any homework of related to this chapter 15, 16. No homework right now. Okay, I want you all to just revise all of this every single day, so that you don't get confused, and keep solving your previous chapters. Now this Wednesday, you can ask me all the doubts of chapter 12 or maybe earlier, later, does not matter. But we will take test on chapter 12 on this Wednesday. So just make sure that you ask all the doubts of chapter 12. If we feel like there were a lot of doubts of chapter 12 and we are not able to clear all of them, then I can postpone the test. But we'll try to clear all doubts of chapter 12 on this Wednesday first. Okay. So again, go through chapter 15, chapter 16, this chapter 17 before we start our tomorrow's lecture. Okay. We'll end it here. Okay.
Thank you.
Welcome. Bye.